Welcome everyone. So let's wait for some time to see if anyone joins. Then we can start. So we'll wait for some time to see if other people join. Then we can start in about 2-3 minutes. I think we can start. So welcome everyone. This is NOC 26 NPTEL tutorial session on semiconductor devices for next generation FETs. The course instructor is Professor Sudeb Dasgupta from IIT Roorkee. I am Debashish from IIT Kanpur. So we are now at 11th week, right? So let's begin. So the first question is calculate the effective width of the FinFET with the height and width of the channel is something like this. So what is a FinFET? So you have your planar FET like this, right? This is your body terminal. This is your source drain. You have gate oxide over here. So yeah, you have your gate oxide here. This is your drain. This is source. So this structure we have studied. This is called bulk MOSFET. Then we also studied another structure. So there we have source drain, and below that we have buried oxide. This is my substrate. This is, let's say, p-type body. I'll have gate oxide. This is drain. This is source. So what is this structure called? This is called silicon on insulator MOSFET, right? So note that this is my single gate structure. This is my double gate structure, right? This substrate terminal can also act like a back gate because I can have field effect from this side as well, right? It is just like a two MOS structure joined together, right? Then I have something called FinFET. So how does that look like? So if you see, mm, so let's say by the way, let me just point. This is length direction, this is width direction, and this is the thickness direction, right? So your MOSFETs are in 3D, it will be in this direction, okay? So think that the structure is in this way, right? So now let's say, so it will be something like this, and then you will have your gate oxide like this. So this is your gate oxide. So this constitutes your gate, okay? And source and drain are in this direction. So if I just extend this, so current is flowing into the channel. That means this is your width direction, Y, and this is your X direction. Okay, so your source and drain will be, let's say, in this side it will be, let's say, source, and in the other side of the plane, into the plane, the currents are flowing. Okay, so this is kind of, you can say, mm, this is one, this is two, this is three. So your channel is wrapped around by the gate in three direction. Okay, this is also sometimes called tri-gate structure, or gate is surrounding the channel from three direction, or This structure is also called FinFET. Okay, and of course, this will be your uh, body terminal. Let's say these fins are extending till this, and as these will be of the same type, so these are your, in another term, this is also called bulk FinFET, right? There can be an SY type as well. For that, you need to do just put a box, for example, put a box here. So that type that we call SY FinFET. So it comes in two flavors. Okay. So why is it called FinFET? Any idea?
Yes, sir. Because there's a fin-like structure coming out of it, right?
So what is fin? So what do you mean by fin?
Is it something like that extension of gate?
No, no. So what is this
Fish?
exactly? So have you seen this?
Yes, sir. That's a fin.
That is called a fin.
Hmm.
So this channel looks like this guy, fin of a fish, right?
Hmm.
In the ocean, you might be seeing that when sharks are traveling, that fin is outside the water most of the time.
Yes, sir.
So that is your fin. So this is why this structure is called FinFET. It
Hmm.
is just a nomenclature that they came up with. So this structure was proposed in 1999 by a team in UC Berkeley, Professor Chen Ming Hu's team, and it was adapted to industry in 2011 in 22 nanometer technology by Intel. So we'll discuss these things, that why this got adapted and what is the motivation behind this, right? So one thing you understand, that this is for to support scaling. Scaling we have discussed, right? Lowering the channel length to increase drive current, but that comes with a penalty of increasing off current, right? Or increasing leakage. So to support scaling, so they proposed this kind of structure. So why I mentioned this timeline is that what is the it is around 12 years, right? So you see, when the device was first fabricated and demonstrated, from that point to mass production or mass commercial production, it took almost 12 years. So that means what? Whatever the devices that we are fabricating today in the research laboratories of universities or some interdisciplinary industry and university research labs, so those technologies will come around 2035 or 2036, right? That is the timeline you have to understand from research to market. Okay, so we design and this fabricate devices for the future to keep the semiconductor industry moving. That is how the semiconductor industry works. So anyway, so did you understand that in this diagrams, this is the length direction and this is the width direction, right? Similarly, here also, this is the width direction, this is the length direction, channel length and channel width. But in this structure, this is the width direction and this is the length direction. So is that visually clear to you? Then I'll move to my next point.
Yes, sir.
Fine. So now let's say what we have is, let's say 300 millimeter silicon wafer. Okay. So let's say it will be a silicon wafer of dia 12 inch. So that is your standard ruler, long ruler that you use in schools, right? So now let's say a very small IC I have fabricated on that, and let me just zoom it to it. And let's just for the time assume that has this particular block has one transistor. Okay. So that means I'll see something like this. So let's say this is how your bulk MOSFET diagram will look like. So this is your W of the channel and this is your length of the channel, right? This is where I am looking from. I am looking from the top. The top view, you will see only a rectangle, right? Which matters to us, the channel region. This is the projection of this gate. So let's say it will be something like this. So this is your W. So this is your W, this W, and this is your length, channel length. So now if that is clear, so what about in case of SOI? In case of SOI as well, I will see the same thing. This is my W and this is my channel length. Fine. But what about FinFET? Let's say, mm, let's take the example. Let's take, I want to have, let's say, 90 nanometer. Let's say W is, let's assume W is 90 nanometer and length, let me assume 30 nanometer. Okay. So this is 30 nanometer by 90 nanometer. So in case of FinFET, how will it look like? So what is the area? So if I zoom in case of FinFET, what is my effective W? My effective W is, just follow these green lines, okay? My effective W is this entire stuff, right? Because what I can do, I can just open it up and it will expand to the entire width region, right? Are you getting what I'm telling?
Yes, sir.
So this is the entire W, the periphery of this green curve. Now let me consider I only have this single fin. This is called fin. So, and to accommodate W of 90 nanometer, uh, so let me just zoom it up and draw it here. So I have a fin structure like this, okay? And then I'll have, let's say, the oxide. Fine. So, and this is where my current is flowing inside the channel. Now, this guy, this dimension is called, so this is like this. So this dimension is called H fin, and this dimension is called W fin, right? So what is my effective W? That goes into that ID equal to half mu n Cox W effective by L effective VGS minus VTH whole square. What is this W effective in case of FinFET? Can you just look at this diagram and tell me?
WFin plus 2H fin.
That will be W fin plus 2H fin. Okay, so now let's say I want to distribute this 90 nanometer between this W and H fin. Let me take one combination. Let me consider my W fin is 10 nanometer. So what will be my H fin? H fin is 40 nanometer, right? To get W effective of 90 nanometer. Just an example. Is that okay?
Yes, sir.
If that is fine, now tell me what will be the size of this box in case of uh, this FinFET. What will be the size of this box?
Nandi.
So what
W
is,
effective is 9
this
AG.
is my uh, L, channel length will remain same. Channel
Hmm.
length, remember, is in this direction, right?
Yes, sir.
So channel length is remaining same. That is my 30 nanometer.
Hmm.
And but what about the W direction? What W I'll look from the top?
WFin.
Exactly. So what is my now W? W is W fin. That is 10 nanometer.
Hmm.
Fine. Now understand that what I am doing basically, if I have to make the same performing MOSFET with bulk technology, I am consuming a area of 30 by 90 of this die, this area. But in case of FinFET, I just need to spend a fraction of that. So 30 by 10.
Hmm.
So now, assuming that I am having enough spacing, so I can have multiple FinFET in the same silicon wafer. So what I am doing essentially, I am increasing the density. I am increasing the transistor density in the MOSFET. That
Hmm.
is what Moore's law was all about, right? In a given area, how much transistor I can accommodate. You see the advantage of FinFET.
Yes, sir. We can have
So
multiple transistor
yeah,
density.
so basically what we are doing, we are taking advantage of the, so how many dimensions I had? I had three dimensions, right? But we always talk about transport in this plane, this XY plane only we are talking about the transport. But in case of FinFET, what I am taking advantage of? I am taking advantage of this other direction, other dimension, that is the z direction, right? So what I am doing, think that I am pinching this semiconductor, think it of a soft ball. I am pinching it, and that region is getting higher. So essentially, what I'm doing, I'm taking advantage of the third dimension. So this is will be hearing about this term 3DIC. Okay, so this is where the first concept of 3DIC was in place. Okay, so 3DIC is nothing but take advantage of the third dimension or vertical dimension. Okay, so that is what is my FinFET. Now that is all from the density or area point of view. We need to understand why from electrical and performance point of view this will also matter. That surrounding the gate from one direction, two direction and three direction, why does it matter? This will lead to the next topics what we will discuss or has been discussed in the course. That is your nanosheet, fork sheet, CFET. These are very simple concepts if you understand the fundamentals of it. Okay, so that is what we will try to do in today's session. So what about this question? To answer this question, this much is sufficient. So what is W effective in this? W effective is 2 times 42 plus 8 nanometer. That is your 92 nanometer. So essentially what you are doing in FinFET, 92 nanometer by whatever length, I am converting it to a silicon footprint. So this is called footprint. So silicon footprint of 8 nanometer times whatever the L that you have considered. Fine?
Yes, sir. Sir, in this
Yeah.
case, width of fin, WFin is equal to just 8 nanometers, right, sir?
Yes, W fin is 8 nanometer.
Okay.
So now the question is, why did we go for FinFET? So one thing is that your density is increasing, that is very good. W is increasing, effective W is increasing significantly over a given silicon footprint. But my scaling generally does not concern about W, right? It generally concerns about shortening the length. What about shortening channel length? So as length decreases, threshold voltage decreases, I of increases. Do you agree to that?
Yes, sir.
So higher static power dissipation. What does that mean? Your mobile phones or your laptops are draining out battery even when they are not operating, right?
Mm.
Or your
Yes, sir.
inverters, whenever they are not switching, that means in the idle state, you have certain leakage which is draining your battery, and that is not good because this whatever this uh, this small technology nodes. That means what? Where we stand today? Where do we stand today?
Sir, I'm thinking something like less than 5 nanometers.
So, okay, so currently industry is it at 3 nanometer technology node.
Hmm.
So what does 3 nanometer technology node means? What does this 3 nanometer mean?
So it means its channel length is approximately 3 nanometers, right? So
No,
the from source to drain is approximately 3 nanometers.
no, that is the wrong concept. What most of us have been learning from a long time, right? Think it in this way. So this is very important to clear this misconception. Channel length, LCH, there is a hard limit of it has to be greater than equal to 10 to 12 nanometer. It cannot be less than that. Why? Because so this is your drain and source, right? This is source, this is drain. So what will happen if I okay, so let me just draw the band diagram quickly. So in off state, your band diagram will be something like this, right? This is your EC. I am drawing the band diagram at this level. So this is nothing but source, channel, drain. Fine. And what direct dimension we are talking about? We are talking about this dimension. This is your LCH. So what happens if LCH goes to smaller dimensions? I mean, let's say what happens if LCH becomes like this?
So tunneling will occur, right, sir? Higher
Exactly.
tunneling.
So what does tunneling, this tunneling is called? This particular tunneling, let me just use another symbol, another color. So this particular tunneling is called DSDT. That is direct
Source to drain.
source to drain tunneling. Why is it bad?
So that means current will flow even when it's supposed to be off, right?
Right. That means what? Okay, my drain is controlling the current
Then get
of the transistor, which is very bad.
hmm.
Right.
Correct.
So this is just a no-no.
Hmm.
So channel length never goes below. What is the channel length? If you see, there is something called IRDS roadmap. You just you can search international roadmap for device and systems or device semiconductor devices, whatever it is. So you can just search it, and they predict the technologies till, let's say, 20 years from now. Okay, you see what is happening, that your channel length for 3 nanometer technology is standing around at 14 nanometer LMIN. Okay, so earlier when we had used to have, like, let's say till 22 nanometer 22 nanometer or 28 nanometer technology, till that point we could tell that, yeah, this technology node definition and the LCH mean are almost analogous, which it was not. It can be higher or lower than that. For example, I can, for a 90 nanometer technology, I can have lower channel length than 90 nanometer. Okay, but what does it 3 nanometer mean then? This 3 nanometer means on a wafer, two metal lines if I draw. So let's say I draw two metal lines. So from the center of this metal line to the center of this other metal line is called pitch. This dimension or the width of the metal line, minimum of that is around 3 nanometer. Okay, it has nothing to do with the channel length as of now in today's technologies. So be very
So does
careful
that
about
mean?
it.
Mhm.
Yeah,
So does that mean it's the distance between the two sheets or pitch? That is what you mean by 3 nanometer technology.
two sheets of metal lines.
Okay.
Okay, these are metal lines. Okay, so is that clear? So you will never commit that mistake that 3 nanometer means channel length is 3 nanometer. It is just not possible. Think logically. Your
Yes, sir.
source to drain tunneling will just kill it.
Hmm.
Fine?
Sir, I have a theoretical question, sir.
Yeah.
Sir, they say that we can move to 1D metals by nanosheet FETs and nanosheet wires and all.
1D,
1D materials.
2D materials, not 1D.
Hmm. So is it possible to go to 1D and 0D materials in the future actually?
Uh, it is present, by the way. Let me tell you in this way. So, okay,
Hmm.
how do I put it? Have you seen graphite?
Graphite, that material in pencil
Yeah,
slits.
pencil lead, right?
Yes, sir.
Do you know how does that structure look like?
There's one 2D hexagonal structure or something like that.
So, it has some hexagonal structure
Arranged in a
like
sheet.
this. Okay. Now,
Hmm.
what actual structure looks like? This, if you copy this, so there are multiple layers of this, and those are connected to. Okay, this is a little bit shifted. So these are basically connected vertically. Okay.
Hmm.
So if you touch the pencil lid, what do you see? It is slippery, right?
Yes, sir.
So let's say this is your layer 1, this is layer 2, this is layer 3, this is layer 4. So what are the atoms in these positions? What is the material of graphite? Carbon,
Yes, sir.
right? So now, why that materials get slippery in your hand? Because whenever you rub your finger on top of that, this layer slides on top of this layer. Okay, the layers between the this one sheet or one layer slides over the another layer. That is why you feel that slippery. So now in 2004, a very interesting thing happened. So two scientists, one is your Henry Game and another is I do not know his first name, some Constantine, Novoselav Constantine, something like that. Okay, so they did what? They took a graphite sample and used a scotch tape. Scotch tape, you know, right?
So you mean quartz?
Scotch tape,
I'm not really sure what that means.
cellotape, you have heard of
Oh, yes, yes, sir.
that thing, adhesive thing, right? So
Okay, yes, sir.
they used to just put it on that graphite sample and rub it off. So by that measure, they were able to secure or isolate one particular layer of this graphite sample, which they call graphene. Okay,
Hmm.
so this material, if you think of, this is how much atom thick? This is one atom thick, right? So it will be like just a sheet where your atoms are. If I see it from the side view, it will be like this. Now, what do
Hmm.
we call this? It will
1D.
have length. It will have this. So this is in the hexagonal direction, right?
Yes, sir.
But the thickness is at one atom length.
Hmm.
So let's say this is W, this is L, and
Hmm.
this is your thickness. That is the radius of the carbon atom.
Hmm.
So whenever your L and W is much more than this thickness, let's say T, you can effectively ignore the third dimension. So this is how it becomes a 2D material. So graphene is the first 2D material. So you understood the concept,
Yes, sir.
why it is called 2D.
Yes, sir.
Now the concern is that it may not be one atom thick, right? Right. I can have a two, three layers as well.
Hmm.
But then also the thickness dimension is so small that I can effectively say that this is 2D materials.
Hmm.
This will play important role, let's say around 15 to 20 years from now.
Hmm.
Okay,
Yes, sir.
fine.
So is it
So,
similar? Is it also possible to go to 1D material similarly like that?
so what do you mean by 1D?
That would be just one line, right, sir?
Okay, so what is 1D? Okay, so if you are going to that direction, so what is 1D? I need to isolate either W or L, right? I need
Yes.
to omit one dimension.
Yes, sir.
So let's say I have a chain of atoms.
Hmm.
This becomes your 1D. So
Hmm.
how does it happen? Let's say I have some uh, something like this. This is called CNT,
Hmm.
carbon
Nanotubes.
nanotubes. So what is happening in nanotube? I am omitting, let's say, the W direction.
Hmm.
So this becomes effectively 1D.
Okay.
For transport, I need only one direction, right?
Yes, sir.
So this is 1D. Now you
Hmm.
can have 0D as well. What is
Indeed.
0D? You have to omit that length direction also.
So
So
that will
there
be
is
individual atoms, right, sir?
individual atoms,
Hmm.
right? So
Hmm.
these kind of things are called quantum dots.
Hmm.
I don't know if you have heard of it or not. So these are used in resonance applications and various other applications. Okay.
Hmm.
You can vibrate this atom and create resonance surrounding it, and that can be used in multiple applications.
Hmm.
So this is your 0D.
Hmm.
Fine.
Hmm.
Okay. Let me just remove all of this. Okay. So what we were discussing? Yeah. So how does it happen and why does it happen that L decreases, VTH first tell me this one. Why does it happen? If VTH decreases, I of increases. Let's say, so do you agree to this diagram? So this is your gate, This is your channel. This is your ground. This is C depletion. This is C ox. And this is if the potential here is delta VG, the potential here is delta psi S. Can you connect? Are you familiar with this? So this is N plus, this is N plus, this is P, this is oxide, this is gate.
Yes, sir, I can understand.
So you will have oxide layer here.
Hmm.
So this is your C ox, this is your
Hmm.
C depletion, right?
Hmm.
And this is the location of the channel. This is the location of the channel. That is this point. Fine. So now can you tell me what is del? Okay, just let it tell del psi s by del Vg. What is this quantity?
Sir, that will be 1 by SC depletion divided by 1 by SC depletion plus 1 by C
1
oxide.
by SC depletion divided by 1 by SC depletion plus 1 by
SC ox.
SC ox. So what does that translate to? Is that clear?
Yes, sir. Hmm.
So this quantity is called, so your N is defined as 1 plus C depletion by C ox. This guy is called slope factor. Okay, we'll come to that why it is so. Is it clear? This is just a
Sir.
definition. I am calling it eta.
Hmm.
Okay. So what is eta minimum? 1, right?
Yes, sir.
And when will that happen? When my C depletion is very small,
Hmm.
right? Okay. So now, uh, okay. So now what is psi s? Can I write this as some constant plus Vg by eta? I'm just integrating this. Is it okay?
Yes, sir.
Right. So, and IDS in subthreshold is proportional to Ns. What is Ns? The total semiconductor charge. So this is semiconductor inversion charge. Let's remove this. Normally it will be like this, and that will be proportional to what? We know that exponential psi s by phi t. So phi t is nothing but kt by q. So if you are not familiar with phi t, I can just make it Vt. You have seen this, right? That your this goes like this. This is your Q versus psi S. You have seen this plot, right?
Yes, sir.
So this inversion charge is basically exponential throughout, and this is your depletion charge. So if I just plot inversion charge, or let's say if I just plot your n of s or inversion charge, it will be exponential function of psi s. Fine. Now, so can I write this exponential of Vg divided by eta Vt from this relation? I can write that, right?
Yes, sir.
Now, in subthreshold, what is the definition of a threshold voltage? Let's say log ID, and this is VGS. Okay. So what is the definition of threshold voltage? So I generally take a constant current and then determine what my threshold voltage is. So that constant current is generally taken at 100 nanoampere times W by L. Have you heard of this?
Yes, sir. Subthreshold slope.
No, no. 100 nanoampere times W by L is the current.
Hmm.
So that means if my W by L is equal to 1, understand this very carefully. If my W by L is equal to 1, then threshold voltage is that gate voltage at which IDS is equal to 100 nanoampere. This is irrespective of whatever W and L you have. Right? Now let's say if you are increasing your W by L, so your current will also increase. Right? Let's say in this case W by L is equal to 10. So now what? How will your threshold voltage, how will you calculate your threshold voltage? If I calculate it in the same line, in this same line if I calculate, so threshold voltage will be much lower here. Constant current method. So that is why I need to shift this line also upward. So W by L I will have somewhere here my constant current. And what will be that value of current now? 100 times 10 nanoampere. That means 1 microampere.
Yes,
So
sir.
it takes care about the WL scaling as well. Okay. This is the definition that industry uses.
Hmm.
They may use 200 nanoampere times W by L, but that it will be around that region 100 to 300 nanoampere times W by L. Whatever the gate voltage gives you this amount of current, that will be your threshold voltage. Is it clear how the industry calculates threshold voltage? Because they do not, they you only are able to see the terminal characteristics,
Hmm.
right? You are not able to see what is your phi b, what is your phi ms. Those are some fabrication point of view. They are setting, but that those things can get altered during the fabrication process. So the norm industry uses is that 100 nanoampere W by L is your threshold voltage. That current level, that gate voltage which gives this current level. Fine. Is that clear?
Yes, sir.
Now, can I, from this information, can I write the IDS equation as 100 nanoampere times W by L times exponential Vg minus Vth divided by Nvt. Is it okay? Just put Vg equal to 0. What is your I? How will you get your threshold voltage? Let just put Vg equal to Vth. So what is your IDS? Does it match the definition?
Yes, sir.
Right?
Mm.
So if that is so, so what is your I of? I of is the current where your gate voltage is 0 and Vd is set to VDD. So whatever we are discussing so far is for long channel transistor. So my in my IDS equation, I'll not have any VDS dependency, right? In long channel transistor. So my I of is what now? 100 nanoampere times W by L times exponential minus VTH divided by NVT. Is it clear?
Yes, sir.
So are you able to see that if my VTH goes down, my I of will go up,
Mm.
right?
Yes, sir.
So what do you think we should have? So one thing is that my Vt is Kt by Q. Let's say T is equal to 300 Kelvin, that is constant. So I do not have the temperature knob to tune up with. So how can I lower my I of? I of can be lowered by, doing what? Increasing Vt. And what are the other options we can have? This quantity is constant. This I have one option. This is constant. So I have eta, right? Eta if I can lower, then also my IF will reduce. Are you getting this?
Yes, sir.
So what is, so this is not a good option. Why it is not a good option? Because if I increase my Vt, what will happen? My ion also will reduce. Power consumption will increase. I need to go for more higher gate voltages to turn on the transistor. That is not good. Now this N or eta. So this eta is what? So from this equation, let's say from this equation, let's write this equation again. IDS equal to 100
Sir,
nano.
isn't
Yeah,
it an intrinsic parameter, sir, actually?
sorry.
Sir, isn't it isn't it like a unique parameter specific to every type of material, actually?
Eta is this.
Mm-hmm.
We'll discuss how to tune eta, okay,
Mm-hmm.
and how it is helping. See, our goal is to understand why we have moved from this to this
Mm-hmm.
and this to this. Okay, that is what we want to understand.
Yes, sir.
So, if I write the equation, it is exponential Vg minus Vth divided by eta Vt. Right now, if I increase Vg by, so let's say T equal to 300 Kelvin. Let's go step by step. Let's say 3 equal to 300 Kelvin, that means room temperature. So what is your Vt? 26 millivolt, right? Are you aware of that?
Yes, sir.
Then my this equation becomes what? 100 nanoampere times W by L e to the power Vg minus Vth divided by eta times 26 millivolt. And also remember this, e to the power 2.3 is equal to 10. Okay, we'll remember this. Now, to increase IDS by a factor of 10, how much Vg should I increase? That is the question. Can I write it 60 eta times 60 millivolt? Can I write this? Just cross check. So how will I cross check? Let's say IDS 2 is equal to, okay, let's say IDS 1 is equal to 100 nanoampere times W by L exponential, let's say Vg minus Vth divided by 26 millivolt times eta. Fine. Now I have IDS2, that is 100 nanoampere times W by L exponential this Vg plus 60 millivolt times eta minus Vth divided by 26 millivolt times eta. So can I take everything out and write IDS1 times exponential 60 by 26? That is IDS1 times e to the power 2.3 or 10 times IDS1. Is it clear?
Yes, sir.
So this guy is called your SS, sub threshold swing. Okay. So this SS is defined as 60 millivolt times eta divided by T by 300. Let's see if I just normalize the temperature, it will give something like this. So if it is absolute scale, I can just remove the unit. So this is nothing but the inverse of the slope of this curve. Okay, slope of this curve is S, that is del log 10 ID divided by del Vg, and SS is S inverse. Okay, you can check the maths, but from the conceptual point of view, just understand this. So what is happening? What is SS minimum at t equal to 300K? From this equation, can you tell me what is SS minimum?
So it will just be 60 millivolt times eta.
60 millivolt times eta minimum.
Hmm.
What is eta minimum?
1.
So this is 60 millivolt. Sometimes it is called per decade because of this 10 factor, right? This we have discussed in one of the earlier session. So minimum subthreshold swing that one can achieve at room temperature is 60 millivolt per decade. This condition is called Boltzmann's limit. Okay, this condition is called Boltzmann's limit. So now my IDS equation, I can simply write 100 nanoampere times W by L 10 to the power Vg minus Vth divided by S. Okay, is it clear?
Yes, sir.
So, sorry, SS. This we have defined as SS, right? So if this equation is clear to you, so now what is my I of? I of is equal to 100 nanoampere times W by L 10 to the power minus Vth by SS. So you see I of minimum will also be the this W by L 10 to the power minus Vth divided by SS minimum. So what I want to do essentially to reduce I of, so to reduce I of SS has to be lowered, or SS has to be approaching SS minimum. Fine. And for that, I want my N to reach N minimum. For that, N is what? N is 1 plus C depletion by C ox. So this quantity, let's say we call it alpha. So I want alpha to be much less than 1. Is it okay?
Yes, sir.
Now let us consider two cases. Let's say this is your single gate device or bulk MOSFET. So you will have your depletion region here, and another case you will have let's say SOI MOSFET. E, and this is your N plus, this is G, D, S. And let's consider this to be fully depleted. So this is bulk, this is FDSOI. Okay. So what will be eta in this case? Or let's say alpha. So alpha is best. So okay, if I draw the uh, capacitor network, it will be C depletion and here C aux. Here gate, this is ground, and this is my channel. Fine. In this case, how will it look like? So this will be ground, this will be gate, this is C aux, this is C depletion, this is C box. And where is my channel? My channel is here, CH. Fine. A general definition of alpha: capacitance between channel to ground divided by capacitance between gate to channel. So what is alpha in case of bulk MOSFET? What is alpha in case of bulk MOSFET from this equation? Bulk MOSFET alpha is this, right? What is the capacitance I am seeing between channel to ground in bulk MOSFET? C depletion. And what is the capacitance I am seeing between gate to channel? Is C oxide, right? But what about alpha FDSOI? What is the capacitance I am seeing between channel to ground? This
C
is
depletion in series
C,
with C box.
C depletion with series with C box
Yes, by C aux.
divided by C ox.
Hmm.
So between these two, this one and this one, which one is lower?
Sir, alpha FDSOI.
Alpha FDSY is lower, right?
Yes, sir.
So alpha FDSY is much lower than alpha bulk. That means what? This translates to eta FDSY is much lower than eta bulk. That means what? Subthreshold slope of FDSY is much lower than subthreshold slope of bulk. This translates to what? I of FDSY is much lower than I of bulk. So you see how it is improved in case of FDSY by means of double gate structure. Now what I want you to do, whenever you read this topic for again or next time, try to think it from the device point of view, that why it is happening. Okay, this is so far we have discussed mathematically and whatever the uh, capacitance coupling is there, but you have to understand it from the physical sense, or you have to get a feel of it, that why it is happening, right? So try to do that. It is not very difficult to understand. So basically what if I plot IDVG in log scale, so if I have bulk MOSFET like this, so how will my FDSOI look like? FDSOI look like something like this. Okay, and this we call improvement of, so basically SS lowering is called improved gate control. What is gate control? That means if I change a very small amount of gate voltage, I can have a huge change in the transistor current. That is your gate control, right? Or transistor control. So if I have that uh, by subthreshold slope, if it is lower, that means if a subthreshold swing, if it is lower, that means my subthreshold slope is higher in FDSOI, because that those are inversely related, right? So that means FDSOI has a better gate control. So FDSOI or double gate structure has a better, the term is gate control, than bulk or single gate transistor. So you have been hearing that if I am controlling the channel region by multiple gates, that means my gate control is increasing. What is actually happening is your subthreshold swing is getting lowered and it is approaching the Boltzmann limit, right? Is it understood?
Yes, sir.
Okay. So that is one thing. Now another thing to consider is your, so what we have discussed so far is this part. But why is this happening? So next question is, if channel length is lower, VTH is lowered. Why does this happen? So this thing is called threshold voltage, threshold voltage roll off. Have you heard of this?
Yes, sir.
What is this?
So as channel length increases, VTH decreases.
Channel length decreases, VT decreases. Why does this happen? What phenomena is responsible for this? So this is one case. Let's say VG equal to 0 volt, VG equal to VTH. This is EC, right? This is source, channel, drain. So I am drawing the band diagram. So N plus P get body, drain, source. I am drawing the band diagram at this location, just at the interface. But what about Let me just draw these lines. So this is, let's say, long channel device. Okay. Now let's say for a short channel device, I'll have something like this. So, so this is short channel device. This is my source. This is my channel. This is my drain. This is L. In this case, this is L. So I can see that my barrier at the source channel is lowered by drain. What is this phenomena called? What is this phenomena called? We have discussed this, right? This phenomena is called drain induced barrier lowering. So this is the consequence of DIBL. Please tell me if this much you have understood. So this location, this is this location, this is this location, this is this location. Please tell me if you have understood this much or not.
Yes,
Then
sir.
I'll move to next.
Yes,
Right?
sir. Hmm.
So now uh, let us think this thing in a capacitive divider network. Okay. Let me just draw this MOSFET in a different fashion that you are accustomed to. And let me just make these junctions very sharp. So let's say this is drain, this is your source. Okay. So this is source, this is drain. And let's say this is your oxide. This is the gate. Okay. And yeah, and let's say that this is your MOSFET. And you have your depletion region, something like this. This is your depletion region boundary, right? So let me just mark the dimensions. So this dimensions is your W depletion. This dimension is your Tox, and this dimension, let's say, is your Xj. So Xj is also called junction depth. It is the source and drain depth, okay, in the PUL. So this is your P type, right, in the PUL. Now, let me, for simplicity, remove this. Understand that there is a capacitance, okay? Now, let's say I have a node at this point. This is the same node, and I have two capacitances. One is this, and another one is this. Okay, this let me call Cox. This is CD, and this is the node in between. Okay, so I am writing an empirical formula. Empirical means not analytical. It is not derived analytically. It can be derived analytically, but for the ease of simplicity, let me just draw the write that threshold voltage of any transistor can be written as threshold voltage of long devices or long channel devices minus drain voltage times CD by Cox. So is this equation okay? So how do you check that? First check that, let's say if VDS equal to 0, my VTH equal to VTH long. Is that clear? Because if my VDS equal to 0, then my curve is, okay, just let me use this. So if let's say VDS equal to 0, so how will my band diagram look like? It will look just like this. Similarly, it will look just like this. Is it okay? That it
Yes,
is
sir.
drain induced barrier lowering, right? There is no
Mm.
drain voltage. So if drain voltage is not present, the barrier height is not lowered, right? That is what we mean. Fine. The
Yes, sir.
next thing is this is some capacitance between the midpoint of the channel and the drain, right? If this capacitance is increased, so if CD increases, uh, influence of VD on this point or channel midpoint increases. Is it okay? Because
Yes, sir.
your impedance is 1 over SCD, right? So if CD increases, impedance lowers, that means this path is more short. That means VD reaches more in the mid of the channel. Fine. Now, if Cox increases, similarly, influence of gate increases. In other words, I can say that influence of VD decreases, right? It is more like a transistor than a resistor. So this equation is in that sense Correct.
Sir, so aim is to increase CX.
Sorry?
Sir, since we want better influence of gate, doesn't that mean we should increase CX?
Yeah, yeah, I'm coming to that. Okay.
Mm-hmm.
So that is not only Seox, okay? There are multiple things. That is what I'm uh, trying to convey. So if we solve two-dimensional electrostatics, the CD is exponential dependence of has a exponential dependence of channel length. Okay, and LD is some characteristic length. For example, it is also called DIBL characteristic length. Okay, that will come to. But can you agree to that? If my channel length increases, the influence of drain decreases. That means effectively I can say that my CD is decreasing. If CD decreases, my drain has less and less influence on the channel. That is what we see in the long channel devices. Okay. And how about COX? How does COX vary with channel length? Very quick question. How does COX vary with channel length? COX is what? COX is
Epsilon
WL
naught.
times epsilon ox by TOX, right?
Yes, sir.
So we whatever we are using in the formulas are COX dash, that is normalized to WL. So COX varies proportionally to L. Fine. Now, so can I write my VTH is VTH long minus VDS times, this is approximately equal to, okay, VDS times exponential minus L by LD. COX I am ignoring, right? What is more dominant, exponential function or linear function? E to the power minus x by x. What will dominate more? This will dominate more, right? So I am ignoring this part. Why? Because this is 1 minus x plus x square by 2 minus x cube by 3. So many terms, right? One linear term, if x is very small, I am just avoiding that region where L is very small. Apart from that, I can remove the denominator L. I hope you understood this.
Yes, sir.
So if that is the case, so for short channel devices, for short channel devices or L lower, VT roll off can be avoided if LD can be lowered. That means what? I can go to shorter channel lengths. Just I have to ensure that LD also lowers, right?
Yes, sir.
Now let us come to LD. So LD is cube root of three quantities: TOX, WDEP, and XJ. LD, if LD lowers, drain is less coupled to the channel, right? So what is happening? If LD is lowered, this entire quantity is lowered. That means this entire quantity is lowered, right? That means my VTH will be very close to VT long. So now from this diagram, does it make sense? So if Tox reduces, I know that my gate control will increase, that you have only told me. So this
Yes, sir.
satisfies. What about W depletion? How come W depletion helps? If W depletion lowers, then my gate control increases.
Yes, sir.
How will that happen? From this diagram, if W depletion lowers, my CD lowers. This CD has to traverse through the W depletion as well. So this CD will be inversely proportional to W depletion, or it is multiplied to W depletion.
Yes, sir. Will be proportional to it.
It is the area of that, right?
Hmm.
Now, so W depletion lowering will also help in my lowering of DIBL. What about XJ? So this capacitance's area is dependent on XJ. If this reduces, the CD area will plate of the CD. This XJ is one plate of the CD, right? So the area of the plate depends on XJ. So if XJ reduces, CD also reduces. If CD reduces, 1 by SCD increases. That means drain influence also reduces. So this also makes sense. So how the device designers go about designing devices and following Moore's law is this. You have to reduce Tox, you have to reduce W depth, you have to reduce XJ. So what are the consequences? Till how much you can reduce? What will happen if you keep reducing Tox? Limited by gate tunneling, right? You cannot reduce this arbitrarily, right?
Yes, sir.
So this led to the invention of high K dielectric or EOT that we have discussed in the last class. What about W depth? Can I keep decreasing W depth? For W depth is what? W
So
depth
it
is
will.
inversely proportional to square root NA, right?
Yes, sir. It will depend on doping.
So it will depend on doping. That means increased doping. What are the consequences of increased doping? Less mobility, because more ionized impurity scattering will be there. So less mobility, and also the most significant thing is VTH also increases with increasing doping, right?
Yes.
So for that, new invention came, we call it retrograde doping. What is retrograde doping? Let's say this is your SiO2 and this is your silicon. It is not uniformly doped. It is doped something like this, okay? Or it will be doped something like this, high at the channel, low at below the surface, okay? So this equation led to many invention or newer technologies. But what about XJ? How can we lower XJ? For example, UTBB FDSOI, ultra thin body and box. So SY we know, right? So this is TSI, this is T box. So in SY UTBB today's technology, TSI is around 6 nanometer, T box is around 20 nanometer, TOX is around 0.8 nanometer, that is EOT. So EOT is different than physical oxide thickness. EOT can be lowered by having a higher oxide thickness so that physical thickness tunneling does not happen, but effective oxide thickness can lead me higher COX values. Fine, but what is the limitation? Increased source and drain resistance, right? Because current is flowing through a very narrow region. If current is flowing through a very narrow region, your resistance will increase, IR drop will increase, which is not good. So this led to the invention of raised source drain architecture. That means what? In FDSOI, if you see, if this is your so if this is your source and drain and this is your box very thin and this is your oxide, this is gate, let's say. So your source and drain are made raised like this. Okay, so that your TSI remains same, but your source and drain thickness increases and current, this resistance is not lowered. Fine. So these are one of the who has joined at this hour. So this is one of the consequences of this equation. This is basically this particular equation led the laws of scaling. So they got a balance of this all the three dimensions. This understand that these all are vertical dimensions. Okay, and they come up with new technology nodes. For example, this was at 45 nanometer technology. For less mobility, they used to increase it, they used train. That came in your 90 nanometer technology. Okay, and so on. So this is what DIBL is. But another very interesting thing, let's say you have reduced your source and drain junction and everything. Now, remember what we were doing so far? The band diagram or EC, whatever we are drawing is at just the interface. That means drain, this is source. What we have been considering so far, that current is flowing just at the interface, right? But this is not true actually. Current will flow in a spreaded fashion. Okay, current flows not just at the interface but at a spreaded in a spreaded fashion, in a spread fashion in this vertical direction due to quantum mechanical effect. Okay, because your inversion charge centroid is not at the interface but it is somewhat lower deep into the bulk. So what are the consequences? So we have, if I draw the band diagram, So we were able to control this DIBL by means of having control over the LD. That is fine. I have controlled my leakage. I have improved everything. But what about this? What about these regions? If I draw a band diagram at this location, no, I may still have drain induced barrier lowering. Why? Because my control of gate is reaching till this point, but not in this region. So this particular region we call leakage region. Okay, my gate control is not reaching till that leakage region. So what do we need to do? The solution is we need to ensure gate control is present all over the channel. Okay, no leakage path is left without the gate control. Fine, that is what we need to ensure. So what is the best thing to do? Best thing to do is add another gate. Have a oxide here, add another gate here. So that way this region is now under the gate control. So this issue is now removed, right? So what is better than two side? This is called gate on the top, gate on the bottom. But I can have, if I keep lowering my length, I know my LD has to go further lower, right? If I have L lowered to avoid the threshold voltage roll off, I need to have lower LD. So for lower LD, I have to keep reducing these guys. However, there is a limit to that we have discussed. So what we can do, we can wrap the channel from another dimension as well. So that is what we have done in FinFET. Now if that is my fin structure and this is the oxide, and let's say this is my gate and this is channel. So what can I see? I can see that my gate has control from all direction, right? So no leakage path inside the channel is left out of gate's control. So that is why covering or surrounding the channel from multiple direction with gate is very important as we go to lower dimensions. Is that clear? So basically multi-gate structure improves gate control. I hope now you understand what do we mean by gate control. One is that subthreshold slope thing. Another, everything is related. Another thing is that I do not want my leakage to be controlled by drain. I want it to be explicitly under the influence of gate so that I of can be lowered by lowering this LD. Threshold voltage lowering can be stopped and so many things. Fine. So these are the motivations behind the invention of FinFET. Okay. Now, as we are going to much lower dimensions, remember where we at FinFET 22 nanometer, then till 14 nanometer technology, we could achieve that. But what about if I want to go to much lower dimensions? Then I need to go to another novel structures that why am I leaving this fourth direction? Why am I leaving? So people started to surround the channel from multiple region, from all the in FinFET I had surrounding by three directions. So this is something called gate all around structure, okay, or GAA. So this is my channel 1, this is my channel 2, this is my channel 3. So source and drain is inside the screen or outside of the screen. So this is the direction of current flow, right? So in that case, in no way we are leaving the channel outside gets influence. Okay. So this can be, this channel shape can be like this, circular. So we call it then GAA nano wire. So it can be like sheet. The channel structure can be like a sheet. So we call it nano sheet, GAA nano sheet FETs, right? And from that, so fork sheet and CFET we'll discuss in the next session. Okay. So just for your understanding, today's technologies or 3 nanometer technology and some technology node beyond that will use this kind of nanosheet structure where this is your gate and then there will be substrate here. Okay. So in a nanosheet structure, which point has the least gate influence? So this is gate, all are connected to the same potential. Let's say this is my VG. This is gate, right? And these structures, as all the gate directions have the same potential, we call it CMG, common multi-gate. FinFET is also common multi-gate. SOI is IMG, independent multi-gate, because this is another two separate terminals. Okay. So last question of today, what is the point or region which has the lowest gate influence in this nanosheet? Which point in this nanosheet, or let's say in this channel, is farthest from the gate? It is,
Of the center.
yes, the center, right?
Hmm.
But understand that this sheets are so narrow that it does not matter if it is so deep into the nanometer, single digit nanometer ranges. And mind it, this is not your channel length, right? Channel length will be in this direction.
Yes, sir.
Okay. So this is not your channel length. Channel length will be in this direction, which is of the order of what is the minimum we have discussed today? 10 nanometer. That is the hard limit. Okay. It will be at the 12 nanometer range. The periphery of this can be very small. Okay. Single digit nanometer. But what about the then what I am seeing if I look at my source and drain, so I will have this. If this is source, this is drain. So this is channel 1, this is channel 2, this is channel 3. So I can have IDS is equal to I channel 1 plus I channel 2 plus I channel 3. So if I use the same current formula, I know that the area of this plus the area of this, or sorry, the periphery of this plus the periphery of this plus the periphery or perimeter of this, adding them will give me the W effective, right?
Yes, sir.
Yeah. So this is where we stop today. So I hope you understood what is gate control, why do we need to surround the channel from multiple direction, and what are the design consideration. Whatever it is, if you understand only this equation from today's session, that will be sufficient. This is the key point that led the multiple sequence of technology development, technology
Mm.
node development. Okay.
Sir,
So yeah,
sir, I just want to ask one non-technical doubt actually, sir.
sure, please go ahead.
Sir, for this, for our coming NPTEL exam, have they actually released the admit card? Because in the announcement section when I went on last week, they said that they will release the admit card, but it's so far not been released.
See, I do not have any idea about the exam, but
Mm,
however, I would request you to raise this question in the discussion forum. Or do
mm.
you have the email ID of the NPTEL team?
I don't think so, sir. No.
So you just drop me an email asking for the email ID of the NPTEL team. I'll just
Okay.
share with you their email ID and you can ask them directly there, right?
Okay, sir.
Okay. So yeah, I think let's conclude today. We had an elaborate discussion about how we evolved from single gate to double gate to tri-gate or FinFET technology, and then followed by nanosheet. And we'll see what some nuances with the nanosheet technology and its subsequent subsequent generations. We call them fork sheet and whatnot, CFET, complementary FET. See, if you understand drain induced barrier lowering very well, you are good to go for and punch through channel length modulation. If you understand these things very clearly, understanding new technologies will be just piece of cake. Fine. So focus on the basics, fundamentals. These are just structures and you just need to know how and why we went from this to that, right? That way you'll be able to connect. Okay, I think we
Sir,
can stop. Yeah.
sir, for our final exam, do we need to learn the fabrication step, flow and all?
There may be some MCQ question on that. Just you
Mm.
need to know what is ALD, right? For
Okay.
example, what is ALD? You don't need to understand what actually ALD is or E-beam lithography is, or how do I say, ultra UV etching and all, right? You just need to understand that ALD is atomic layer deposition. By this, I
Mm.
can have precise deposition of gate and of gate oxide materials. Right?
Okay,
This
okay.
much only will be sufficient.
Yes, sir.
Yeah. So, okay, let's stop it here.